All right, so let's go ahead and get started with the second part. So the second part, we're going to talk about graphing or, yeah, kind of sketching or graphing their derivative from data. Okay, so in data, we don't actually have a defined function f of x, right? We do not have an f of x, so we can't use like any of the, we can't use this, nor can we use so we can't use either one of these, right? Because we don't have an actual function. So we have to look at the data. And if you look at the example number 5, it says, suppose 30 people are in a room. What is the probability that 2 of them share the same birthday? Okay. And it shows there the probability of the shared birthday. So you can actually sketch this function if you would like, all right? But you're not going to have a numerical function or something like this, okay? So you have to come up with a rate of change for each different place, okay? So let's go take a look at room and people between 0 and 5. From 0 and 5, you had what? 0, 0, and then you had 5.027. So you had 2 points, right? 5 and 0.27. So I need to find the rate of change. So the rate of change is nothing more than delta y over delta x. So we're going to have what? 0.027 minus 0 over 5 minus 0, right? So this is going to be what? This is going to be, if we calculate it, that's going to be 0.0054, okay, which is a point there. But look at where they put it. Do you put that at 0 or do you put that at 5? What's the appropriate place to put this number at? And the part that they're going to use is this, since we don't have a certain point, we're going to use the midpoint. The midpoint between 0 and 5 is 2.5. And that's why if you look at there, it says the midpoint of the interval, 2.5. So the change is going to be 0.0054. The next was between 5 and 10. Again, so it's going to be what? So I'm going to have 10 minus 5. And at 10, it was 0.0117. Minus at 5, it was 0.027. Right, I'm going to do this. And I'm going to place this at where x is equal to 7.5. Okay, if you do that, you're going to get what? 0.0180. And if you graph those points, okay, you're going to find, so the one on figure 3.6 is the scatter plot of the original data, right? If you look at that, what's happening to the slope? The slope is going what? So if it's going to look, it looks like this, right? So it's going to start at close to 0, go up, 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 and it's going to come to a point here. And then once it passes that point, it starts to go down, down, down. So it's still positive, but it's so from here, it's more positive, more positive, more positive until you come to the point of inflection. And then it's going to become less positive, less positive, less positive like that, right? So if you flip the page, you can see that is on page 106, figure 3.7. You can see that the graph peaks out at that point of inflection point. It looks like it's about at 20. So at about 20 is where it peaks out, and then it goes back down to it gets closer and closer to 0. Okay? So that's how you would do this. So this is how you would take data and draw the derivative of that function or that data group or whatever you want to call it, right? Okay, all right, so that's that. This is one of my favorite questions to put on a test because it kind of gives me an idea if you actually understand the meaning behind a derivative. Okay, just kind of put that out there, all right? Now we're going to talk about one-sided derivatives, one-sided derivatives, one-sided derivatives. Okay, And example number 6 is going to give you the one-sided derivative where y is equal to x squared when x is less than 0, y is equal to 2x when x is greater than or equal to 0. Well, it's greater than or equal to on this side, not that it matters. So the graph's going to look like what? The graph is going to look like when it's less than 0, it is a parabola. And then on this side, it's going to look like this. Okay? So if you look at the derivative, on this side, it's easy, right? Because the derivative is what? The slope. The slope is constant. It's constantly 2. So your derivative is going to look like this. 2, like that. Your derivative is going to look like that. Over on here, I have what? X squared. So I'm going to go here, very negative, less negative, less negative, less negative, less negative, close to 0. So it's going to be very negative. And it's going to be then what? Close to 0, right? Like that. Like that. Okay. So what's happening here? The derivatives are what? What is my derivative here? What is the tangent? If I'm going to draw a tangent line here, how am I going to draw that? Is it going to look like, it has to go through this point. It's going through this point. It's still tangent, but there are several different ways it can be tangent, right? Okay. In other words, the derivative coming from this way and then coming from this way are different. Because coming from this way, the derivative is what? It's going to get closer and closer to 0, right? When it's coming from this way, it's always going to be 2, okay? So what does it say? It says, since the left-handed derivative is equal to 0 and the right-handed derivative is equal to 2, the derivatives are not equal at 0, and this is just like the limit, okay? There is no derivative at this point, okay? So whenever you see a graph that has a hinge point like this, okay, you do not have a derivative here. Okay, all right. Wow, can you guys even see that with the sun? All right, anyway, okay, so we're done. You're done with part 2.